Hello, everyone. This is Professor Jian. I'm going to talk about some basic calculus facts about exponential functions and their applications in probability theory. The first very important fact is that e to the x, the derivative of that is itself. Okay, so it's antiderivative e to the x dx would be itself plus c. So these are the two important facts about e to the x. If we add a little bit flavor to e to the function, let's say the differentiable function e to the x, and then we have a chain rule e to the h x, then you have a h prime x, and then you do the antiderivative, you have h prime x e to the h of x dx, that equals e to the h of x plus c. All right, so let's use these simple facts to work on the problem. Example 1, say we have a density function, f of x equals c times e to the negative 3x, and x is greater than 0, less than infinity. We didn't specify that the function 0 at negative numbers, it's implied. So first thing is how to find c. Because it's a density function, we have this fact about density function. For any density function, integral from negative infinity to infinity should be 1. All right, so we plug in this function, which is c times e to the negative 3x. Be very careful. Once you plug in this function c times e to the negative 3x, you must change the lower limit to 0 because it's 0. The function itself is 0 when x is less than 0. So you cannot keep this negative infinity here. That would be wrong. And then we just do the integral. Okay, so let's move out c. That's a constant. And then we have e to the negative 3x dx. One way you can solve this is to use substitution, but I'm not going to do that. You can; it's not bad. But what I want you to recall is that we have a h prime x e to the h of x. Integrate it, you will get e to the h x plus c. And we have a definite integral here, so c is not important. But the thing is that I need this thing in front of this e to the negative 3x. But the derivative of negative 3x is very easy. It's negative 3. So what I'm going to do is to make it something like that. So I have I multiply by negative 3, e to the negative 3x. Then I divide by negative 3. Let's move it out. Times 1 over negative 3. So I didn't change anything. Okay. But then we know the antiderivative of that is e to the negative 3x. So I have a c. Let's move this negative 1/3 in front. And I have e to the negative 3x. It's antiderivative, right? From 0 to infinity. For probability, when we do the probability, you don't really need to use a demi-variable, let x to be m, and let m go to infinity. Just keep in mind that you're taking limit when m goes to infinity, and we know e to the negative 3 times infinity is 0. That's the limit is 0. Yeah, so we simply write 0, and then we have a minus, and you have c times negative 1/3 e to the 0, which is 1. Okay. Don't forget, there's a negative sign here. This negative sign will be canceled out by with this negative sign. So in the end, I have a c times 1/3. because it's 1, so I know C equals 3. One possible careless mistake is that you forgot some negative sign somewhere, and you got C equals -3. That cannot happen because this is a density function. The density function is always non-negative. You can't not have a negative sign in front of a positive function. E is a positive function. And so this is never a density function, right? Especially when x is from 0 to infinity. Okay, it's not a density function. All right, so this is one way to get C instead of using substitution. Essentially, it's the same, but you can use substitution if you feel comfortable. It's just I think this method is faster. All right, let's do another problem. Let's try to find the probability of some. So we add something here. So x is a random variable. It has a density function of that. So let's calculate the probability of x greater than or equal to 4. Okay. So it's an integral from 4 to positive infinity. And C is what? C is 3. So 3 times e to the -3x dx. We know the entire derivative of that is negative e to the 3x. Okay. Oh, but you should have negative sign here, but then, I multiply by -1, it doesn't change anything. This is actually antiderivative e to the -3x. You have a negative sign here, so you have a negative sign here. Okay, that's what I did, but that was the reason that there's a negative sign here. And you have 4 to infinity, so plugging infinity gets 0. Minus would be, this minus would be canceled out. So the answer would be e to the -3 times 4. It's a very small number, so I'm going to skip the exact answer. That's e to the -12. All right, so let's talk about a general distribution like this kind of form. This is called exponential distribution. Exponential distribution. F of x equals lambda. Lambda is a parameter like 3 at the beginning. In the previous example, negative lambda x, and x is greater than 0. And it's implied 0 where x is less than 0. Let's look at the CDF f of x. By the definition, you have a PDF and integrate it from -infinity to x. Let's change this x to t, so there will be no confusion to x otherwise. So t will disappear in the end. Again, when you plug in lambda times e to the negative lambda x, you must change the lower limit to 0, and here x again, it's t. dt. The entire derivative of this is negative e to the negative lambda t. Again, if you don't see that, put the negative sign here and the negative sign outside, and this will be the entire derivative. The entire derivative of that is e to the negative lambda t, but then you have a negative sign here, you need to keep it. All right, then you evaluate it from 0 to x, and then you have a negative e to the negative lambda x, minus minus becomes positive, so it's 1 minus e to the negative lambda x. Another interesting or important concept, it's very easier to use, more convenient than the CDF, is called survival probability. Survival probability, which is the probability that x is greater than or equal to little x. So it's the probability that something, some x random variable, that will survive beyond x. By the way, the meaning of x, the random variable, could be the lifetime of certain things, so the lifetime of a bulb, etc. I will talk more details about exponential function in another video, if I don't forget. But for the moment, just use it as an example to review some calculus. That's the point. So that equals 1 minus the probability of x less than little x. So it's the distribution is continuous. So you can really change this. It doesn't really matter. So you have a e to the negative lambda x. Okay, this is easier to use. I don't have a 1 minus in front of it. It gets called the survival probability. That's one thing. It's the derivative and antiderivative of e to the x, or e to the negative some number times x. There's another calculus when the integration technique, which is the integration by parts I want to introduce. It's very useful in exponential distribution. Integration by parts. That's it. Integration by parts. No, just parts by parts. The reason of integration by parts comes from the product rule of derivatives. So you differentiate u times v, and you have a u prime times v plus u times v prime, and then integrate both sides. Let's do the antiderivative or indefinite integral. And you have a u times v prime dx, whatever, it doesn't matter. Just do that. All right, sometimes we're looking for this, but it's difficult to find directly. This is probably easier. So we can get that. We can get this u prime v equals, and integral of u prime v equals integral of u v prime minus u v prime. It's a derivative, antiderivative. Then you cancel out both. You have a u times v. I don't need to put the plus c here because this is antiderivative as well. It has c involved, so I don't need to do that. So I have this equation, which is exactly what antiderivative is. Sorry, what are the integration by parts? Exactly what integration by parts is. All right. Now let's have a look at an example. Let's find the mean of e of a exponential distribution, so lambda times e to the negative lambda x greater than 0. So let's find the mean. We have a random variable which has a density function that. So the mean e expectation of x is defined to be the negative infinity to infinity x times fx dx. But then when you plug in this lambda times e to the negative lambda x, you need to change the lower limit. You have lambda times e to the negative lambda x dx. This is a typical example of using integration by parts. Sometimes you will see integral of x e to the x squared, negative x squared over 2, or something like that. And then you can see this is very close to the derivative of negative x squared over 2. So for this kind of integral, you should use the substitution instead of integration by parts. But here, the derivative of negative lambda x is just negative lambda. You have an x here, which is annoying. So we want to get rid of that. So we can treat this as, let's see, we wanted to find u prime b, and you have a ub minus ub prime. We can consider, let's see, I don't want this to be u because later on you consider this as the derivative of x squared, half x squared. Then next time you get a bigger power, it's getting more complicated. So instead, I'm gonna use this as v, and this is u prime. Okay, so we do need the antiderivative of that, but we just discussed that. We do x times, treat it as a negative e to the negative lambda x, and then prime. I add the negative sign here because you differentiate it, you would get that lambda. There's no negative in front of this lambda. Okay, so you do need a lambda, a negative sign in front of the antiderivative. And then I use integration by parts. I keep this x. Okay, you have u, right? You have a catch v is x, and u and u is this negative e to the negative lambda x, and value from 0 to infinity. This is the integration by parts, indefinite integral version. If you have a definite integral, you simply do, so you have a, b here, you simply do a, b here, and you have a, b here. Okay, so that should be, it's a part of calculus. All right, it's a bit messy there. Move down. Minus integral from 0 to infinity, and now I can take the derivative of x, which is 1. And then I keep that thing, the negative e to the negative lambda x dx. All right, and then you plug infinity, now x goes to infinity, but e to the negative lambda x, when x goes to infinity, this goes to 0 faster than x, or kills that infinity. So multiply together, you get 0 actually. So the 0 minus 0, it's just 0. Well, x plugging, you plug in 0 to x, you get 0, so it's just 0. And you have negative, negative canceled out, you have a positive. You have that. You know this density function? It's defined on x greater than 0, so the mean has to be greater than 0. This is a positive function, so integrated, you get a positive number, that's good. When I make a mistake. But if you have a negative sign in front of it for some reason, and you know that's a mistake, there's a mistake, because then you would get a negative mean, which is not possible. Okay, so when you do the problem like that, you keep tracking if you have if you made a mistake somewhere. We need to make the derivative of negative lambda x, so negative lambda times e to the negative lambda x. I multiply by that to make this to be the derivative of e to the negative x, negative lambda x. And then I needed to divide it by negative 1 over lambda. Okay, so I'm not doing anything, I just multiplying by 1. The equation will still hold. Now, I have a negative 1 over lambda. Don't be afraid of this negative sign, because eventually it will get canceled out. And I e to the negative lambda x from 0 to infinity. You plug in infinity, e to the negative infinity will be 0. Oh, by the way, I didn't specify that lambda should be greater than 0. Otherwise, it's not a density function anymore. It's implied, or should be specified. Then we have 0 minus, then we have a negative 1 over lambda, so positive 1 over lambda. So negative, negative. This positive comes from this negative sign, and minus. Okay, and e to the 0. E to the 0 is 1, so it's just 1 over lambda. All right, so that's the mean. And in order to find the the variance, the standard deviation. You have e to the x squared, and you have x squared somewhere here. You just do the integration by parts twice. It may be a little bit more complicated, but there's some small trick you can use. I'm not going to talk about here. So that's, I think, one application of an exponential function here. I wanted to move on to another topic, application. The Taylor's expansion of e to the x. E to the x, the Taylor expansion, 1 plus x squared over 2 factorial, dot, 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 plus x to the n over n factorial, forever, okay, forever. This is Taylor's expansion of e to the x. Now let's look at the Poisson distribution. It's one of the important discrete PMFs, Poisson distribution. The density, not density, PMF, the probability mass function is this f of k, let's use k, e to the negative lambda times lambda to the k over k factorial. K is 0, 1, 2 integers. People probably don't have difficulties remembering this PMF and the mass function. Just remember you have a chain, okay? E to the negative lambda, then you have lambda to the k, and then k factorial. So you have sort of have a chain. If you do that, it's probably easier to remember. Lambda is a parameter. Lambda is a parameter. This is a PMF. Okay? We actually can use this fact from calculus to prove that. So we want to show this f of k is a PMF. First of all, it's non-negative. That's no problem. An important part that you need to prove that it is a PMF is you need to show that the summation of f of k, the k from 0 to infinity, should be 1. That's what we want to prove. Okay. So let's plug in this PMF to the summation. So I have a summation of e to the negative lambda times lambda to the k over k factorial, and k from 0 to infinity. That is e to the negative lambda. E to the negative lambda is a constant with respect to k, so you can move it out from the summation. So I have a k from 0 to infinity, lambda to the k over k factorial. But then you see, that's exactly what we have here. Change this, change this x to lambda. So this is just e to the lambda. So we have e to the negative lambda times e to the lambda that equals 1. Okay, so that by that we showed that this is indeed a probability mass function. These two, so you have this lambda, and exponential distribution also has lambda. They are closely related. One, we can show that these lambda, they match. One way of looking at it is this. You have a exponential function, exponential distribution, which is e to the lambda times e to the negative lambda x greater than 0. And you have a fk of a Poisson distribution with also e to the negative lambda times lambda to the k over k factorial. k equals 0, 1, 2, so forth. We know the mean of this exponential distribution is 1 over lambda. The mean mu and e of x equals 1 over lambda. What it means is that when lambda is bigger, this function goes to 0 faster. So it's like steeper than when lambda is smaller. So this lambda is bigger, this lambda 2 is bigger than lambda 1. Okay. And probability, the tail probability would be smaller for that one. The mean would be smaller because the density function of exponential distribution is like talking about lifetime of something. So if lambda is bigger, f goes to 0 faster, then you have a expected shorter lifetime. So you have 1 over lambda. Yeah, so it's sort of reciprocal. When lambda gets bigger, you have a shorter mean lifetime, and you have a 1 over lambda, which makes sense. I'm not proving that, I'm just trying to make sense. The relation between Poisson and exponential distribution, and there's a very nice relation between these two. Poisson distribution is to describe the small probability events. It's a probability of some small probability events. So let's say you have a Poisson process. Let's say starting from 0, then nothing happened. Boom! At a certain point, you have some Poisson event happened, and then you wait another piece of time, and say, boom, another Poisson event happening. So suppose you're like policeman sitting in a corner of a street, and then you try to catch some traffic violation. So you wait, boom, you get somebody. And then you finish that and you wait, when boom, you get another person. So catching a traffic violation is like small probability event. We can treat it like that, or at least we can approximate using Poisson. We can treat it like a small probability event. So the number of small probability events would be modeled by Poisson. And the waiting time would be exactly exponential. So if you have a Poisson process like that, the waiting time would be exponential distribution. Okay, you have another exponential distribution here. Now to model the waiting time. And these lambda would be the same. So let's think about lambda bigger. Lambda bigger, you have a shorter waiting time, and then you have a more small probability events happening in the unit period of time. So this lambda is also the mean of this Poisson. We didn't show that. We can. It's not that bad. Maybe I'll talk more about it when we hit Poisson distribution. All right, so these lambdas match. I think that's about some application of a exponential function in probability theory. Oh, there are more. There are definitely more. For example, the gamma distribution. There's something, for example, the expectation of Poisson is lambda. We can show that. I think I will talk about that later on. This is just introduction about exponential function and applied in probability. That's for today. Thank you. Bye-bye.